And tonight we have a lithograph. This is a brand new one of the Lagoon Nebula Messier 8. And thanks to a person who wrote me and said, hey, can you share that with the online audience? Well, I found it very hard to send paper through the internet. Unless you're Wreck-It Ralph, you can't be traveling through the internet and bringing things around. But I can share with you the URL of where these lithographs are posted on our amazingspace.org website. So that URL, amazingspace.org, resource page 548, will get you to the Lagoon Nebula, and there is a PDF file of it, and those of you on the webcast can look at it. And you too can say ooh and ah over the pretty picture, and then turn over and read about what that pretty picture is really about, okay? Tonight, we have black holes and other dark matters, which is the reason why I think this place is packed. Because once you put the term black holes in your talk, everyone says, ooh, we got to find out about this, okay? All right. Upcoming, we have January 15th. Now, first Tuesday in January is New Year's Day. Second Tuesday in January is the American Astronomical Society meeting out in Seattle, and I'll be out there, and so will a lot of other astronomers. So we have postponed it yet again to the third Tuesday, January 15th. And it's really good because what Scott will be talking about, some new stuff will be announced at the AAS meeting, so you'll get some really cool new stuff. And he'll be talking about initial exoplanet discoveries with TESS, the Transiting Exoplanet Survey Satellite. You're going to want to hear that because that's cool stuff about exoplanets. February 5th, back to the first Tuesday of the month, Amaya Morrow Martin will be talking about your place in the stars. And in March, we have our familiar TBA showing up again, which means I need to schedule somebody. I might fill in this one myself with our visualization talk. When that is decided, it will be announced up here on our website. If you go to your favorite search engine and search for Space Telescope Hubble Public Talks, you'll find this, and we have our list of our upcoming, links to our live and our archives, as well as our email list server sign up. That email will send you out announcements. We send out about 2 every month, 2 or 3 a month, so not a huge crush on your inbox, and we promise no spam. If you have comments or questions, you can send them to this email, publiclecture@stsci.edu. Social media for the Hubble Space Telescope, for the James Webb Space Telescope, and for the Space Telescope Science Institute on Facebook, Twitter, YouTube, and Instagram. I myself dabble a little bit in Facebook, Google+, and Twitter, but not that much. And tonight, yes, we have the observatory. It's clear enough tonight that we will be doing observing. It's nice and cool, so hopefully the air is nice and still and you have some beautiful seeing. It's one of the unfortunate things about astronomy that the best nights for seeing are freezing cold, okay? So bring some hot chocolate. Irini will be here at the end and take people across the street. We'll probably gather over here on this side of the room at the end. If I forget to announce it, remind me, or I'm sure Irini will remind me. And now our news from the universe for December 2018. Our first story, a stellar hazmat warning. And I told you guys while we were vamping that OSIRIS-REx was a tortured acronym. Hazmat is a slightly tortured acronym too, and I'll get to that in a minute. But let's start with the Hertzsprung-Russell diagram. How many of you taken Astronomy 101 and know the Hertzsprung-Russell diagram? How many are going, oh my gosh, is he going to give a lecture now here? All right, okay, class, this is the Hertz. No, I don't need you to understand the Hertzsprung-Russell diagram, except to recognize that this is how astronomers organize all the various stars in the universe, okay? It's got temperature on one axis and luminosity on the y-axis. And the important thing here is that the brightest stars, the most luminous stars, are up on the left, and there's this diagonal track leading down to the lower right, which we call the main sequence. And the most luminous stars are few and far between, whereas the least luminous stars, the red dwarfs in the lower right, are all over the place, okay? The meek have already inherited the cosmos because there are so many more red dwarfs than there are blue giant stars, okay? And so the red dwarf stars, the ones in the lower right, the red ones, the low luminosity ones, the low temperature ones, they are actually extremely important because they are the most numerous stars in the universe. So if you're going to be looking for planets and life in the universe, they matter an awful lot, okay? Another thing that matters about stars is that stars have energetic activity on them. This is an ultraviolet light image of a solar prominence. All right, now many people mistake this and call this a solar flare. It's not a solar flare, it's a solar prominence. And there's magnetic fields that are spewing all sorts of energy around on the surface of the sun. And there are things called solar flares. They don't look like this. They look like this. And these are magnetic reconnection events that send out tremendous amounts of energy across our solar system. We also have things called coronal mass ejections that send particles at high energies. And we have what we call in our solar system space weather. And some of our satellites are out there to monitor the space weather. And you may have heard that sometimes when one of these coronal mass ejections or something is sent in the direction of Earth, it hits our magnetic field and sometimes can disrupt our communication satellites. Okay? Or if the astronauts are up in the space station, they need to get inside and protect themselves, okay, when one of these solar storms come in. However, that's just for a sun-sized star, and the sun is a medium-sized star. These small stars, these red dwarf stars, can have much more energetic activity. And that is when we get to hazmat. So this is a study on habitable zones and M dwarf activity over time. Can you see how you get hazmat out of that? Yeah, okay. But the acronym is actually appropriate because they're studying how volatile these M dwarfs, the red dwarf stars, are, and could they affect the planets forming around them and perhaps life forming on those planets. And what's important is to take a look at stars at different ages. This is the activity over time part of it, okay? Looking at, billion-year-old red dwarfs versus, a few 100 million years old versus tens of millions of year-old red dwarfs, okay? And what they found in this study, and basically these solar flares are easiest to see in ultraviolet, so that's why you need Hubble to do this, because Hubble, being above Earth's atmosphere, can see the ultraviolet light. And they looked at a population of 40 million-year-old stars. Okay, now, 40 million years old is old for you and me, but it's young for a star. These are just born stars. And the energy in the solar flares was 100 to 1,000 times stronger than it was for the billion-year-old stars, the old stars. So there's a lot more energy happening. And this has interesting implications for planets formation because at 40 million years, that's when Earth-sized planets will be forming, terrestrial planets will be forming. So these M dwarf stars, the most numerous stars in the universe, have appear to be very energetic just at the time that planets are forming. So if you want to form life on them, could this M dwarf activity be effectively hazmat? Could they interfere with the formation of life on these planets? And this is not a conclusive study in terms of that it actually does or does not, but it shows that we have to not only think about how we form these planets around a star, but we also have to think about the activity of the star itself while those planets are forming. So this is an interesting study that will, I'm sure, be followed up much further in the future, trying to look and understand, this whole process of planet formation that, we are still, just really, it's so exciting how much we're learning about this process as we go on. All right. Our second story is the ghost of Cassiopeia. This is the constellation of Cassiopeia in this beautiful image from Akira Fujii. It's that W you see in the center there. Okay, Cassiopeia is a wonderful constellation for those of us in the northern hemisphere because it's circumpolar. It's always around the North Pole and just circles around the North Pole. So most times of the year, you can find Cassiopeia on the night sky and find that W. And that center star in the W is known as Gamma Cassiopeia. And Gamma Cassiopeia is illuminating some of the gas around it. Sort of the faint red blotch on the left is called IC59. And that bright one down bottom that looks sort of like a mountain, that is IC63. This is a wonderful image from the astrophotographer Robert Gendler. And you can see that the mountain in IC63 is pointed towards Gamma Cas. All right? That shows that it's the ultraviolet, the energy from Gamma Cas that's sculpting that gas, that's blowing away the low density gas and ionizing the gas to make it glow. And Hubble does various pretty picture release images. And when we did our pretty picture release image, going through the various pretty pictures, they thought that this looked like a ghost. And so we released for Halloween a picture of the ghost of Cassiopeia. And I don't know, it looks more like a hooded shroud or something like this, but it's really kind of cool. So this is what they call the ghost of Cassiopeia. Not to be confused with the Ghost Nebula or the Little Ghost Nebula or like 3 other things that are called Ghost Nebula type things, but they nicknamed this the ghost of Cassiopeia. We took this light invisible. We also took a image in infrared light. And to give it that really spooky feel, we created an animated GIF that goes back from visible to infrared. And that was sort of a Halloween pretty picture release, The Ghost of Cassiopeia. And that's our news for this evening. Now we go to our main speaker of the night, and our main speaker tonight is, let's see, where are we? Did we get there? Yes. Okay, our speaker tonight is Dr. Marc Kamionkowski, whom I had the extensive pleasure of working with up at Columbia University. I was a postdoc working at Columbia, half-time at Columbia and half-time at the American Museum of Natural History when Marc was up at Columbia. He did his degree at Caltech and Chicago. Right. All right. I thought I confirmed that it was Caltech. I'm wrong. Okay. It's all right. At Chicago, and then went to Columbia. And after a few years, he missed me so much, he decided he'd come down to Johns Hopkins. Not quite. He came down, and he's in the department across the street at Johns Hopkins University. He is one of the celebrated cosmologists and real big expert on the cosmic microwave background, but he's not going to talk to you about that tonight. Instead, he's going to talk about cosmic ripples from black holes and the Big Bang. Ladies and gentlemen, Dr. Marc Kamionkowski.
So, let me make sure I'm... Okay, is that good? Okay. So today I'm going to talk to you about dark matter, but the story is actually going to begin with the discovery of gravitational waves from a binary black hole system 2 years ago. And this is work that began in the cafeteria here in Azafran in January of 2016. The rumor started heating up in the astrophysics community that LIGO had detected something and there was going to be an announcement and it was going to be big. And so I was sitting around the lunch table with some of my collaborators and we were thinking, well, we got to think of something interesting to say because this is going to be big. And we started brainstorming and we came up with the most ridiculous ideas you can possibly imagine. And at some point we came up with an idea that was ridiculous, but not completely ridiculous. And so we decided to write a paper. And in brief, and what I'll tell you over the next 40 minutes is that we simply postulated that the black holes that they discovered might actually be the dark matter that we have for a long time known to exist in the universe, but we have no idea what it is. And it was a crazy idea, but as I said, not completely crazy. There was an interesting coincidence that popped up when we considered this possibility. And so we wrote this paper, and a lot of people found it interesting. It's gotten a lot of attention over the past 2 years. Do black holes like the ones that LIGO detected make up the dark matter? As I'll tell you, we don't know. 2 years ago, I was fairly optimistic. Things have developed since then. I'm a little less optimistic, but the jury is still out. So the title is Cosmic Ripples from Black Holes in the Big Bang. Cosmic ripples refers to the gravitational waves I'll tell you about. Black holes refers to black holes, and the Big Bang is the Big Bang. Please interrupt me if there are questions. This is gravitational waves, general relativity, black holes, dark matter. It's not rocket science, so everyone should be able to understand. So the story begins February of 2016. There was a front page article in the New York Times that pointed out the gravitational waves have been detected. And it was beautiful timing because Albert Einstein realized that gravitational waves should exist almost 100 years before. He sort of put the finishing pieces of his theory of general relativity at the end of 2015. And the gravitational wave signal was actually detected in September of 2015. So, very, very nice coincidence. This discovery was absolutely spectacular. There's nobody in science who is so jaded as to say, they detected gravitational waves. What's the big deal? Actually, there is a story I have to say. So this was a huge discovery, and there was a press conference online that the NSF was broadcasting. And some people in the physics department had set up a seminar room like this one, so we could play it on video and everyone could come and watch. And some people sort of got donuts and coffee and were milling about before the thing started. And there were 2 undergraduate students walking by, and one of them was heard to say to the other one, "What's going on here?" And the other one goes, "Oh, I don't know, they discovered gravitational waves," or something like that. And the other one goes, "Whatever." So. Anyway, it was one of the quickest Nobel Prizes ever awarded. These people also received the Gruber Prize, the Kavli Prize, the Shaw Prize, and the Breakthrough Prize. Any possible scientific recognition or honor that is available immediately went to the team that discovered these gravitational waves. And as I said, this phenomenon was sort of predicted by Albert Einstein's theory of general relativity. And this goes back 100 years to 1915. And the basic idea of general relativity is the following equation. And I'm always told that I shouldn't show equations in popular talks. But I like to show equations because I'm a theoretical physicist. This is really all I have. I'm not an observational astronomer. I don't have pretty pictures of nebula and things like that. This is the best I can do. We're really proud of it. But the point of an equation is that there's an equal sign in the middle. There's something on the left, and there's something on the right. And the thing on the left is supposed to be the same as the thing on the right. So this is known as Einstein's equation, and Einstein wrote this down. And this encapsulates the theory of general relativity. And it's simple and elegant because the thing on the left is a capital G with some Greek letters on there, and the thing on the right is a capital T. And I remember I first learned this equation when I was a senior in college, and I was taking a general relativity class. And I passed by a professor I had for a quantum mechanics class. And he said, "How's it going?" I said, "It's going great. What are you taking?" "I'm taking general relativity." He's like, "What do you think?" I said, "So simple and elegant, G mu nu equals T mu nu." He goes, "Yeah, but what's G mu nu and what's T mu nu?" Yeah. So anyway, this actually has a fairly simple interpretation. G mu nu, the thing on the left, describes the curvature of space and space-time, and the thing on the right describes the matter content of the universe. And so this describes a picture that looks like this. So according to general relativity, space-time can be bent. and distorted. And the distortion of space-time is given by the presence of massive objects. So massive objects distort space-time. And this equation tells you how that works. The space-time curvature is related to the distribution of massive objects, which is T mu nu, the matter content on the right-hand side. In words, what this says is that space-time tells matter how to move, and matter tells space-time how to move. So the second thing I told you, so matter tells the space-time how to curve, and then the curvature of space-time tells you how objects move. And I'll show you better pictures of this in a second. But you know, if a particle is going to go along a straight line in this curved space-time, it couldn't go along a straight line. The trajectory is actually deflected if the space-time is curved. If I take a very soft mattress and I put a very heavy bowling ball somewhere in the middle, it sort of pushes that mattress down. And then if I try to roll a ping pong ball past that bowling ball, the trajectory of the ping pong ball will be deflected by the curvature in the mattress. So that's basically what general relativity tells us. Space-time tells matter how to move, and matter tells space-time how to curve. That's the essence of Einstein's equation. This was an incredible mathematical insight back in 1915. There was absolutely nothing in that existed in physics before this to foreshadow this or to build up to it. It sort of came out of absolutely nowhere. But it turns out that the theory is correct. And Albert Einstein actually realized the theory was correct almost immediately because there was one anomaly in planetary dynamics in 1915, which was the perihelion advance of Mercury. So it turns out that Mercury's orbit around the sun, like that of most planets, is not perfectly round. It's actually elongated. According to Newton's laws, according to the inverse square law that Isaac Newton derived or wrote down back in the early 1700s, late 1600s, these ellipses should close in on themselves. But what was found is that Mercury's orbit does not close in on itself. It sort of precesses. It sort of rotates around in this direction over here. And it's a very tiny and subtle effect, but it had been measured quite well to be 2 degrees per century. And Albert Einstein realized that these equations that he wrote down could account for this perihelion advance. And so there's a story that he couldn't sleep that night because he was so excited that he actually realized that this ridiculous equation that came out of nowhere was actually correct. We also know it's correct because of the existence of gravitational lensing, or the bending of light. And this was verified in a famous expedition by Sir Arthur Eddington in 1919. So it turns out that the gravitational field of a massive object like the sun will actually bend the trajectory of light. So, if you send a light ray out in the middle of nowhere, the light ray goes straight. But if you send it near a massive object, the gravitational field of that massive object will actually blend the trajectory of light. And this is something that's difficult to actually verify because the sun is so bright that you can't see the stars behind it. But if there's an eclipse, if the moon passes in front of the sun, then for a brief period of time you can actually see the stars behind the sun. And so Eddington verified this deflection of light during a solar eclipse in 1919. So I think I said in 1916, very shortly after the original theory was proposed, Einstein realized that the theory predicts the existence of gravitational waves. And here's a movie that I will show you, and I'll show you another version later on. And the basic idea is that there is a gravitational field due to a massive object. So if I have one planet over here, that gives me a gravitational field. If there's a second planet over here, that also has a gravitational field. And the gravitational field due to the presence of 2 planets is going to be the sum of that from this one and the sum of the gravitational field from here. Now, if I have a binary star system, if I have 2 stars that are gravitationally bound and spinning around each other, or, for example, if I have a planet-star system like the Earth or the planet Jupiter spinning around the sun, I will have something that looks sort of like this. Now, as those planets move around each other, or those stars or black holes or whatever massive objects you have move around each other, the gravitational field is going to change. And so that's what we see over here. So if I'm sitting over here, the gravitational field that I see due to those 2 stars changes. If you're looking at a pair of stars over here, you'll see one gravitational field. If you see them over here, you'll see a different gravitational field. And as they spin around, you will see a time-varying gravitational field. That time-varying gravitational field propagates outward as a set of ripples in space-time. So something like this may be non-intuitive originally, but it shouldn't be too non-intuitive. The surface of a pond, if it's still, is very flat and peaceful and calm. But it can bob up and down. And if I drop something in the middle of this pond, that disturbance will propagate out as a series of waves. And suppose I have a toy boat sitting at the edge of the pond. These waves will propagate out, and the toy boat will be sitting there still, but at some point the waves will pass by, and that toy boat will start to bounce up and down. So if I move the fluid over here, somehow, those waves propagate out, and they are detected because they then induce motion in some test object, like this toy boat at large distance. If I have a tight string, and I shake it, and I disturb it on one end, that disturbance will propagate out in this direction as a wave. And suppose I have some beads on the string at the other end. Those beads will start to move up and down as the wave encounters them. So again, a string is a medium that can carry wave-like motions, or carry waves. And the way I induce those waves is by shaking the string up and down. And the way I detect those waves is through the motions that those waves induce in a set of test masses. The same thing is true for radio waves. Does anybody actually listen to the radio anymore? Okay, back in the old days, there was something in your car called the radio. You could turn it on. And the way the radio works is that there is a transmitter. You see them, for example, in TV tower. And roughly speaking, there are a bunch of electrons. And each electron, when it wiggles, sends out an electromagnetic wave. And the way I detect that is that if I have an antenna, like in my car, the wave, as it hits the antenna, sets free electrons into motion. And then, your receiver detects and amplifies those motions. There's one more example. Usually we think of the ground as rigid and fixed. You don't think of the ground as shaking and moving around. Well, in California you do. But here you generally think, well, the ground is fixed. I can walk across it, it's not going to shake, it's not going to move. But you've all been sitting at home at some time when a very heavy truck rolls by. And on a bumpy road, that heavy truck bounces up and down, and you can feel the shaking in your house. So although the ground seems to be very rigid, in fact, it's not perfectly rigid. And if you have something that's sufficiently massive that starts shaking, the ground will transmit waves, and you will then feel them. Since the ground is so rigid, that thing has to be really heavy to actually shake the ground. And when the ground does shake, it doesn't shake a whole lot. You feel a slight tremor, but it's not a huge thing. It turns out, as Albert Einstein predicted, and as we now know, due to all of these experimental verifications of general relativity, that space-time, which we always think of intuitively as being perfectly rigid, every position in this room can be specified by three numbers, the numbers on a Cartesian grid. The position in that direction, the position in that direction, and the position in that direction. And we always in physics imagine a lattice that represents, points in this direction, x equals 1, 2, 3, 4, y equals 1, 2, 3, 4, z equals 1, 2, 3, 4, and the location of anything or anybody in this room can be represented in terms of those three numbers. So space, and space-time, we always think of as being very rigid. But as it turns out that space-time is extremely rigid, but it's not perfectly rigid. And if there are massive objects, they can curve the space-time. And if you shake those massive objects, those will shake the space-time. And if the space-time shakes, we'll feel it. Things will start to move around. So this was all pretty much theoretical expectation until a few years ago. So in 1916, these gravitational waves were predicted. waves carry energy. When the truck drives by and starts shaking, if you're sitting there and your chair starts shaking, there's energy in that motion. So how to get there? Well, the medium, the ground, carried the energy from the truck over to you. So likewise, gravitational waves can also carry energy. They propagate at the speed of light. They were detected indirectly back in the early 70s, and there was a Nobel Prize award in 1993. There was a system of two neutron stars. Neutron stars are very dense remnants of stars. Each one weighs 1.4 times the mass of the sun. And there are several binary pulsar systems that we know about, which are two neutron stars spinning around each other. And it was seen that in one particular system, the two neutron stars were spinning around each other, but they were spinning up, their orbital period was shortening. They were speeding up as they were seen to be speeding up, which was interpreted as speeding up due to the emission of gravitational waves. So the signal from these neutron stars gave us good evidence that the gravitational waves exist, that they were being emitted from this binary neutron star system, but no one had actually seen or detected a gravitational wave. So how do we detect gravitational waves directly? I told you already. Waves are detected by the motions they induce in some type of test masses. Radio waves are detected by the motions they induce in electrons. The ground waves are detected by the motions they induce in the chair that we're sitting on. The toy boat is used to detect waves in an otherwise still pond. Gravity affects masses. And so the way that we detect gravitational waves is through the characteristic motions they induce in a set of freely falling test masses. So the LIGO collaboration actually made a video. This says scale of effect vastly exaggerated, so I don't want to alarm anybody. But they made a video of what it would look like if a very large amplitude gravitational wave were to pass through the Earth. And the video looks like this. So this is a low amplitude gravitational wave, and as we'll see, the amplitude from a binary black hole merger is expected to increase and get faster. So roughly speaking, that's what's happening to the Earth when a gravitational wave signal passes by. The effect was greatly exaggerated. The actual amplitude of the effect is like 1 part in trillion. Pretty small. So, in practice, as I said, the motions are going to be extremely tiny. And so what was done was something called laser interferometry. And so what happens is one of the characteristics of a gravitational wave is that if we have a gravitational wave propagating down in a direction perpendicular to this plane, the masses in this direction will get stretched out, while the masses in this direction will get stretched inward. And so what was people thought to do is to send a beam of light, a laser signal, through a half-silvered mirror that then splits the beam so that one beam goes towards this mirror over here, and another beam goes toward this mirror over here. The two beams then bounce back, are recombined, and then come back over here. And since light is a wave, when these two waves are recombined, they can either add coherently or they can add destructively. And if they add coherently, the light signal that's received over here is stronger. If they add destructively, the light signal over here is weakened. So again, the LIGO people made a very nice movie of this, which I can show you. So there is the beam that gets split, bounces back. It comes back towards the detector, and as these mirrors shake, the light that's received in the detector is either brighter or weaker. And the reason that happens is that each of these light rays is actually a wave, and if the spacing between these two different arms is just right, those two waves will add destructively. And as the masses move around, as the lengths in these two arms change, what was otherwise a destructive interference might become a constructive interference, and then the beam gets brighter. So they have an interferometer that looks like this, and what they look for is variable light brightness at that detector. I am told that this is the most precise measurement ever made by a pretty wide stretch. It was 40 years in the making. From the initial proposal to the detection was roughly 40 years of technology development and science. The detection was made by a collaboration, an American collaboration, LIGO. They also used results from Virgo, although they were null results, which is a European collaboration. There's a British-German interferometer that's being built called GEO. There's a Japanese interferometer being built called TAMA, one in Australia, and there's also one being built in India now. But the original detection was by LIGO, and in the future we're going to have networks of gravitational wave detectors all working together. So LIGO stands for Laser Interferometer Gravity Wave Observatory. This is, roughly speaking, $1 billion of taxpayer money, very well spent. It is the biggest NSF investment, single investment by a wide margin. It's a US-led project. It does have international collaboration. They have two detectors. One is in Washington State, and the other one is in Louisiana. And the reason they have two detectors is that if somebody told you they saw something go bump in the night, you'd say, what was that? You'd say, oh, something went bump in the night. Oh, interesting. But if somebody in Louisiana also says, hey, something went bump in the night, and you say, well, what time did it go bump in the night? Well, it happened precisely at 12:03 a.m. plus 16.48 seconds. And then the people in Washington say, oh, wow, we saw the exact same bump in the night. So they use the simultaneity to reject spurious signals, because things are always happening that shake those masses around. The length of the arms are 4 kilometers, and although there's 4 kilometers between these mirrors, what they detect are motions that are a fraction of the size of an atomic nucleus. So this is a picture of the Livingston Observatory from the sky, 4 kilometers and 4 kilometers. This is another picture, and here is the Hanford Observatory. They're more or less identical. There are subtle differences, but they're more or less identical, 2 4-kilometer arms. And the motion that they detect is illustrated by this movie, which the LIGO collaboration also provided. So this is an atomic, this is let me start again. What you started with was an electron spinning around. Let me go back, because this is absolutely astounding. This is a movie of an electron spinning around an atomic nucleus. So that's pretty small. So there is the atom. And then we zoom into the atomic nucleus, which is composed of a couple of protons and neutrons. And what they actually detect is a motion of that magnitude. So that is incredible. This is not easy. So I was a professor at Caltech for a while, and my office was down the hall from the people working on this project, and they were always like walking past my hall looking really busy because they were going to detect gravitational waves. And every time I saw them walking around, this is what I thought. This is a scene from Fitzcarraldo, which is a movie by Werner Herzog about a man in 19th century Brazil who decides he wants to carry a boat over a mountain. Anyway, on September 14th, 2015, they had upgraded their detectors, and before they were actually going to start doing science runs, they were doing some test runs. So they turned the machine on just to do some tests to see if everything was working. And this is what happened, and there's a soundtrack for this one. So they're constantly measuring the separation of these mirrors with a very, very small time resolution. And the mirrors keep shaking around because when people drive by, that shakes the ground. And when there's a lightning strike anywhere on the planet, that shakes the things around. So they constantly see things in LIGO, and they constantly see things in Livingston. The number of things that affect the Hanford detector and the Livingston detector are pretty rare because they're several thousand miles away. And what they saw, though, at the same time in both detectors is a very prominent signal that looked like that. So here is another plot. So this is the displacement of the mirrors as a function of time in the Hanford. And you see that it goes up and down and up and down and up and down and up and down, faster and faster, and then stops. And you see the exact same thing in the Livingston data. Goes up and down, up and down, up and down, gets big, and then stops. So, this, we are very, very sure, is the signal from a pair of black holes that are merging. So another prediction of general relativity, which was realized first by a guy named Carl Schwarzschild, who was fighting in the trenches in World War I and figured this out while in the trenches and then passed away a few months later. So Carl Schwarzschild figured out that the equations of general relativity allow for the existence of things called black holes. These are the densest possible objects in nature, and they are so strong that they are so dense that the gravitational field is so strong that not even light can escape. So, if I try to throw a ball in the air, it goes up and it goes down. But if I had a really good arm and I could throw the ball at a velocity of 11 kilometers per second, I should know what that is in miles per hour, but I don't. 11 kilometers per second, the ball wouldn't return to Earth. It would actually escape the gravitational pull of the Earth and escape to infinity. A black hole is an object that is so dense, the gravitational field is so strong that the escape velocity from the surface is bigger than the speed of light. And since nothing can travel faster than the speed of light, nothing can escape from the black hole. So, we can take the equations of general relativity and set them up so that there's not just one black hole, but two black holes that are in orbit about each other. And if you do that, what you find is that gravitational waves will be emitted. As the gravitational waves are emitted, those gravitational waves carry energy away. And if they carry energy away, that means there has to be less energy for the remaining system. A bound system of two objects actually has a negative energy. It has a gravitational binding or potential energy. And as they get closer, that becomes increasingly negative. So the energy that's carried away as gravitational waves causes the remaining binary to become closer and closer. And as that binary, as the two stars become closer and closer, they spin around faster and faster. Mercury gets around the sun a lot more quickly does the Earth, and the Earth gets around the sun a lot more quickly than Pluto. So, likewise, when two black holes get closer and closer, they start to spin around each other faster and faster. And when they do that, the gravitational wave frequency increases and the power in gravitational waves increases. And so that is what is seen here. And this is actually a scientific simulation. This is actually full solution of the numerical solution of the equations of general relativity. So that is what they look like. They get closer and closer. Here you see the gravitational waves being emitted. As they get closer and closer, the orbital period will decrease. They'll start to spin up, and the gravitational wave signal will get stronger and stronger. And so this is actually what it looks like when gravitational waves, when two black holes merge. And what's kind of interesting, and I was surprised by when I first saw these numerical simulations, is that when they finally merge, it happens very quickly, and there's a burst of gravitational waves emitted. So it turns out that calculations such as the ones that I showed you here can allow you to predict the gravitational wave signal far away. And that prediction turns out to be spot on what was seen by LIGO. Not only is it spot on, but based on the properties of the signal, the frequency, how quickly the frequency increases, the magnitude of the signal at the merger time, and also the ring down in the final period. From all that information, we can actually infer that one of these black holes had a mass of about 36 times the mass of the sun, another one was about 29 times the mass of the sun. The final black hole had a mass of 62, and 62 minus 36 minus 29 is 3. So they're actually, from special relativity, Albert Einstein, E equals mc squared, energy is equivalent to mass. There were 3 solar masses of energy released as gravitational waves. And we can also infer the distance, which is about billion light years, which is good because because if it was a lot closer, then that movie they showed you of the Earth bouncing around might have been a little more realistic. This is kind of a cute movie. This is actually another movie that they made that illustrates what the sky would look like if you were looking through a pair of a binary black hole system. So the black holes, I told you, deflect the light. And so the image of the stars that are behind the black holes get distorted. And again, this is a scientific simulation of what it would look like if we were a lot closer to this binary black hole system. So as they move around, the lensing pattern would change, and that is what the sky would look like as these things spiral around each other and then merge. And the merger happens very quickly and suddenly, and then there's a very brief ring down any second now. So there they merge, and then there's this final ring down. Anyway, there's a big question, which is the question that we were wondering in the Azafran, in the Space Telescope cafeteria over here in January of 2016, in February. Where do these black holes come from? We detected them. We're very, very sure that that was a binary black hole system that we saw with these gravitational wave events. And subsequent developments have given us even more confidence. But where do they come from? I told you that they can exist within the context of general relativity, but they're there. They're not just mathematical constructions and figments of theoretical imagination. This measurement shows that these black holes actually exist, and they weigh 30 times the mass of the sun. So the most reasonable explanation, and the one that with 99% confidence is going to be correct to some extent, is that they probably come from massive stars. So this is a very busy plot. I don't want you to look at everything, but basically, there are a lot of stars in the universe. Like the sun, some of them are more massive than the sun, like those of you who are paying attention to the details of the Hertzsprung-Russell diagram will remember that there were blue giants, which are extremely massive, and there are red dwarfs, which are very low mass. So what we know is that stars are powered by burning protons into helium nuclei, fission. But there's only a finite amount of fuel that a given star has. And when that fuel runs out, the star dies. And it does not die an elegant death. And the way it dies and the remnant that it leaves behind depends on its initial mass. So low mass stars, like the sun, we're pretty sure that when they use up all their nuclear fuel, they blow up into a red giant for a brief period of time, they then blow off a lot of gas, and they leave behind something called a white dwarf. More massive stars, though, undergo a similar evolution, but when they finally become a giant, instead of just blowing off a nebula and leaving a white dwarf, they undergo this huge explosion where their inner cores undergo gravitational collapse and leave behind either a neutron star or a black hole. So this is something that we're very, very sure about, although the details we don't have a lot of confidence in. But we're very, very certain that neutron stars and black holes are formed as the remnants of massive stars. Now, the issue that kind of surprised us back in 2016 is that each of the black holes that were detected in this original event had a mass of 30 times the mass of the sun. And the mass of the black hole that remains is only a small fraction of the mass of the original star, because most of the mass of the star is blown away in this planetary nebula or supernova. So that means that a 30 solar mass black hole would have had to come from a much more massive star. That's okay. There are much more massive stars in the universe, but if you were paying attention when Frank was talking about the Hertzsprung-Russell diagram, he told you that there are far more low mass stars than there are high mass stars. And so it was kind of surprising that the first black hole binary that LIGO detected came from these very, very, very rare supermassive stars. We would have thought we would see 5 or 10 solar mass black holes, not 30 solar mass black holes. And so that got us to thinking, and I'm not a gravitational wave astrophysicist, I'm not a stellar astrophysicist, I'm not a black hole guy, I'm not a neutron star guy, I'm a cosmologist. And one of the things that I get paid to do is think about what the dark matter is. Fortunately, I don't get paid to actually figure it out, because that can only happen once, and once it happens, we're out of work. So, I think about what the dark matter might be. And so here are black holes. They're dark. They've been discovered. They're out there. Maybe they're the dark matter. So it's a silly idea. So dark matter. This is a mystery that's been around for a good fraction of a century. And the reason we believe in dark matter, there are many, many lines of reasoning that tell us that there's a lot of dark matter in the universe. But the simplest is perhaps what we call galactic rotation curves. So there are a lot of galaxies, like the Milky Way, which are a collection of a gravitationally bound system of stars. And each star moves in the gravitational potential well due to every other star. And galaxies have some finite extent. They are 10 what we call kiloparsecs. And the kiloparsec is roughly 3,000 light years. So here in this diagram, actually, this is 10,000 light years. This is a smallish galaxy. And then the stars sort of peter out. There's not a whole lot out here. But occasionally, you do find some star at large distance or some gas cloud. And you can see these gas clouds spinning around. And you can measure the velocity at which they spin around. And if you plot the speed at which these gas clouds are spinning around this galaxy, it continues to increase at large distances from the galaxy. And that is unusual, because if this was all the matter that we saw, then according to Newton's laws, the velocity should decrease. Right? In the solar system, the sun is a very, very massive object right in the middle. And Mercury, which is right next to the sun, spins around really, really quickly. But as you go further out in the solar system, Pluto takes forever to get around the sun, because Pluto is so far away. So if this was all the matter in the galaxy, we would have expected to see these speeds become much smaller at large distances from the galaxy. But instead, they're seen to increase. And this, along with many other lines of reasoning and many other forms of evidence, suggest that there is a lot of dark matter, non-luminous matter, that surrounds the luminous stuff that we see. We don't know what it is, though. We're very, very sure that it's there, but we have no idea what it is. All we know is that it's dark. It does not emit light, and it does not absorb light. We know now precisely how much there is. I can tell you to within a few percent how much dark matter there is, even though I can't tell you what it is. And we know how it's distributed in galaxies and elsewhere in the universe. I told you it does not emit nor absorb light, so it can't be the same stuff that we're made out of. It can't be atoms. For many years, we've speculated that it's perhaps some new elementary particle, and we've been trying really hard to find this elementary particle, but we have not yet succeeded. And so, it's not unreasonable to entertain other possibilities, and Stephen Hawking back in 1974 and others thought maybe there are primordial black holes. Maybe the Big Bang, when it produced the universe and produced all the stuff in the universe, maybe it also produced a whole bunch of black holes, which survived to become the dark matter today. So we tried to figure out, and these are some of my collaborators. So my work is always done with students and postdocs, and in this particular case, also with Adam Rees, who's a colleague who has a Nobel Prize, which helps with the credibility. So these are all postdocs and one graduate student across the street. So this was the paper we wrote. I don't even remember the exact title, but it was more or less, did LIGO detect dark matter? So it's a crazy idea, it's a speculative idea, but not completely crazy. And this is the coincidence I told you about. So we know how much dark matter there is in the galactic halo. So we know how much stuff there is out here. If all of that dark matter is composed of 30 solar mass objects, then I can tell you how many of them there should be and what the typical spacing should be. We also know how fast these things are moving around. These dark matter objects, whatever they are, in a galaxy like the Milky Way galaxy, are actually spinning around at a speed of several hundred kilometers per second. And we also know that two black holes, if they pass by each other, can actually form, very briefly, a brown system that then spirals in and merges. So roughly speaking, I've got two ping pong balls passing by each other at large separation. They're not going to hit each other. But if the two ping pong balls pass by each other with a separation that's smaller than their size, they're going to run into each other. Same thing is true of automobiles, which is why we have lanes. So we know, roughly speaking, how big a 30 solar mass black hole is. And so it is very, very straightforward to estimate how often these things should run into each other. And so we did this estimate. We did this calculation. And some of these people are actually very well equipped in terms of the theoretical background to do the calculation properly. And so we did it. And it turns out that the rate at which such black holes would merge, if they made up the dark matter in galactic halos, agreed surprisingly well with the rate at which black holes merge that we infer from the fact that LIGO saw one of these events after 2 weeks of observation. And it was that coincidence that led us to write the paper, and it's that coincidence that has been very intriguing for a number of our colleagues here and elsewhere. So I think that this paper that we wrote is the most highly cited post-LIGO, LIGO-related paper. So this is a hypothesis, but it's not the answer. I don't know that this is the dark matter. It's a pretty out there hypothesis. But scientists are supposed to not only propose hypotheses, but try to come up with ways to test the hypotheses. And that has been a very active area of investigation for our group and others. I will not tell you all the things that people have proposed, but I'll tell you about one thing that we suggested and that we're hoping will be done soon. So it turns out that there are these things called fast radio bursts. So you've all seen James Bond movies, and there's the one James Bond movie where he goes to the Arecibo telescope, which is this huge radio dish. You know what I'm talking about? Yeah. Okay. So radio telescopes like Arecibo and a few others detect radio frequency radiation from the sky. And for a number of years, I don't remember exactly how long, but for about the past 10 years, it's been noticed that occasionally there is a very brief flash of radio frequency radiation coming from the sky. So these flashes last less than 1,000th of a second. And for a long time, people wondered whether there was some type of problem with the telescope. But a number of different telescopes started to see these things. They did a number of tests. And it's now very certain that these are actually coming from the sky. And for a variety of reasons, we believe these to be coming from, there are good reasons to believe that these are coming from large distances. So suppose one of these fast radio bursts goes off, and we have no idea, I should say, where they come from. We're pretty sure they're coming from outside the Milky Way, but we have no idea what the source is. Most people think that has something to do with phenomena on the surfaces of neutron stars, but we can't be absolutely sure. But we don't even care for our purposes. So I should also tell you that as of now, there are about 50 fast radio bursts that have been detected. About a year ago, there were about 25 that have been detected, but there is a new telescope that the Canadians have built called CHIME, which stands for Canadian Hydrogen Intensity Mapping Experiment. And unlike the other radio telescopes like Arecibo, which point at a very small part of the sky, this Canadian telescope points at a very large fraction of the sky, sees a very large fraction of the sky, and so they expect to detect these fast radio bursts far more frequently than the past. And in just a few months of observation, they've doubled the sample of fast radio bursts already, and they expect to see several thousand more in the next few years. So suppose there's a fast radio burst, and suppose that black holes make up the dark matter, then there is some chance that there will be such a black hole along the line of sight to a given fast radio burst. And if that's the case, then this massive object, this black hole, can gravitationally lens the signal from this fast radio burst. So the light from this fast radio burst, these radio waves, can travel to us either along this trajectory or along this trajectory. And it turns out that most generally these two trajectories have slightly different path lengths. And the path lengths differ by roughly a millisecond times the speed of light, or a few milliseconds times the speed of light. And so what we predict is that instead of seeing one flash, one sub-millisecond flash, which has been the case for all the fast radio bursts that have been seen, if these black holes are out there, roughly 1 in 100 of them will be gravitationally lensed, and after seeing the original flash, you'll see the flash arriving through a second trajectory. And so you'll see an echo. So these measurements are now being made. As I said, they've seen 50. In a few years, they'll have maybe 5,000. And if black holes make up the dark matter, then they will see several hundred within a few years that have an echo that looks like this. So this is one way to test the scenario. There are other ways to test the scenario. I won't discuss them all. But I think I will close there. So the era of gravitational wave astronomy is here. We're learning all about black holes, about general relativity, how space-time wiggles around. Maybe we'll also learn something about dark matter. I should say the jury is still out as to whether primordial black holes can make up the dark matter. There's still some debate within the astrophysics community about whether they can make up the dark matter or whether current observations already rule them out. So I'm not going to tell you I'm absolutely certain that they can be the dark matter, but we are taking the idea very seriously. Either way, it's a very exciting prospect, and many people are interested in it and trying to pursue further tests of this scenario. Thank you very much, and I'm
questions. We don't have the microphone flash around.
Are we going to get the microphone? Yes, we are going to get the microphone. Here is Grant. Everyone give Grant a big hand. All right, questions?
The Bird et al. 2016. Could you tell us more about Bird?
Bird was
Pages back.
Bird was the Brit. We had a Brit, a Frenchman, an Israeli, American, an Italian, a Spaniard, Greek, and American. And me.
But an online audience can't see the pointer. So if there's something specific, call them out.
So this is Simon Bird is the big one with the glasses. He's so he was just the lead author. It was Simeon.
If you guys want to pass that on down, you can toss it.
I'm a kind of a veteran who's seen a lot of these lectures, and this dark matter compared to nothing. Where does dark matter end and nothing begin?
Oh. That's a tricky question. I would say that we don't actually know very precisely, but we know that in the center of a galaxy, there is a high density of dark matter. And the density of dark matter, which is going to be very big over here, decreases as you go further out. But sooner or later, there's going to be another galaxy over here that has its own dark matter halo. And so it's not clear that there's anywhere in the universe where there is no dark matter, but the density of dark matter is probably going to be smallest in the places between the galaxies.
Is there a place where there is that there is just nothing?
Well, we do have voids.
I don't think so. I would say that there are places where the dark matter density is small, but I don't think there's any place in the universe that we can point to where we're pretty sure that there is no dark matter.
Yeah, I see a basis for a new disaster movie in the making here. Just out of curiosity, you had mentioned or implied that if a solar system was fairly close to merging black holes, that the distortion would be considerably greater. Would there be enough to actually tear apart a solar system?
I don't think so. It would have to be. We went through this calculation once before, when we were sitting in the cafeteria and tossing around crazy ideas. The probability that this would happen is extremely, extremely small. So the rate at which such things occur, as we infer from the LIGO measurements, is so small that it's unlikely that there was ever such an event even in our own galaxy over the entire history of the universe. So these events are so rare that a typical galaxy will go the entire length, the entire universe without ever seeing such an event.
Thank you. I feel relieved. Yeah.
It would have to be very, very close. I think closer than the nearest stars. So.
We have another question.
If black holes were in some way dark matter, how would that relate to the accelerating expansion of the universe? Is there any connection?
That's a good question, and I have no idea. So I was giving a talk about something related this morning to a philosophy class. There's a philosophy of science class, and they just wanted somebody to talk about things that we do in physics. So there's the dark matter problem, and then there's the dark energy problem. And in science, we are always told to look for economic solutions. And so ideally, we would have one theory or model that can explain both dark matter and dark energy. And some theorists have tried to do that, but it turns out to be far more difficult than you would imagine. And what it really winds, all these solutions where they try to merge the two, they really wind up looking like a solution for dark matter and a completely different solution for dark energy that are then glued together. I don't know, but I don't think that I would be surprised if I were to be like resurrected 100 years from now and learn that the solution for dark energy was related to the solution for dark matter. I can imagine that 100 years from now, cosmologists will be looking back at us and thinking, oh, that was so quaint and silly. They thought there was dark matter, there was dark energy. They didn't understand that it was just, but I have no idea what that is.
Yeah, but I mean, our current understanding has the dark matter localized around galaxies, et cetera, whereas the dark energy is sort of throughout all of space. And so that to me, has always been the fundamental problem of trying to combine the two, is that their distribution function is totally different, right?
I agree, and that's how I view it. That's how 99% of people like us view the problem, but I kind of think that sometime in the future there's going to be like a solution that, of which these are two different aspects.
That's a nice, hopeful thought.
I think Stewie answered that. He says vipers are on the dark side.
Yeah.
Thank you. How closely related to Project Einstein is this as far as the detection of gravitational waves?
How closely related is this to Project Einstein?
Yes.
I don't think I know what Project Einstein is.
It is, one part of it is a distributed processing research project using BOINC.
Uh-huh.
Okay, taking data from the Arecibo telescope and from the LIGOs in Louisiana and in Washington, D.C. And they're looking for the, apparently, if I understand correctly, looking at the locations of pulsars where you could do interferometry using the pulsars.
Okay, okay, now I know what you're talking about. That's a very, very interesting set of projects. So there are pulsars, which are spinning neutron stars that are located, 10,000 light years away. And there's a bunch of them spread throughout the sky. And what I showed you was this gravitational wave detector that they'd built in Washington and Louisiana that had two arms. So there was a set of test masses over here that were oscillating like this, another set like this. So it's been proposed to use pulsars for the gravitational wave as gravitational wave detectors. So if I have, if we're on Earth right here, and there's one pulsar over here, and another pulsar over here, and a gravitational wave passes by, the pulsar over here will oscillate in this direction, the pulsar over here will oscillate in this direction. Those two oscillations will be out of phase. And we can detect that in principle. And people are trying to do this. And the principle is exactly the same as LIGO. The difference is that the arm lengths are 10,000 light years as opposed to a couple of miles. And so the wavelengths of the gravitational waves that you can detect are bigger by about a factor of 1 billion. It's a very, 10 years ago, even 3 years ago, I would have put my money that those pulsar timing arrays would detect gravitational waves before LIGO. But they didn't, but I think they will. I think we will see something in the next few years.
Okay, so Mark, there's a question from the online audience that I'm sort of summarizing from things, is they want to understand how many more gravitational waves are out there. You've got black hole mergers, and obviously if you had supermassive black hole mergers, you could see them like that. But the neutron stars, how many other different types of events will these gravitational wave detectors be able to see in the somewhat near future?
So there are binary black hole mergers. There was an event last year that was either a binary neutron star or a neutron star black hole. We don't know which, but we do expect, over the next few years to see neutron star mergers, neutron star black hole mergers. We'll see more black hole mergers. There is a space-based gravitational wave detector that we are considering, that the European Space Agency is leading and NASA is participating in. When that flies, that will detect or have sensitivity to detect mergers of supermassive black holes that each have a mass of 1 billion times the mass of the sun. People have also speculated that supernovae, when a star explodes and forms a neutron star, that there might be a gravitational wave signal from that. People have speculated that some neutron stars might have little mountains on them, and those mountains, the spinning of a neutron star with a mountain might give you a gravitational wave signal. The space-based observatories will also detect gravitational waves from white dwarf binaries. So some of the low-mass stars at the end of their, when they use up all their nuclear fuel, turn into white dwarfs. So if I have a binary star system that consists of 2 low-mass stars, it will evolve to a white dwarf binary. And we actually know of a number of white dwarf binaries. So there are signals from those binaries that we expect to see. I'm sure there are other things, but those are the ones that we generally hear most about and are the most promising.
So really gravitational waves just are studying the interactions of dead stars with the white dwarfs and the neutron stars and black holes. So Stars got to give up their lives in order for gravitational wave astronomy to work, right?
Exactly.
All right, do we have more questions up here? Yeah.
There was a famous interferometry experiment in the late 1800s, Michelson-Morley, when people were looking for the ether.
Yep.
What would have happened if this interferometer, LIGO, had existed back then and had gotten this reading back then?
So it is exactly the same type of interferometer that they use, but has, trillions of times better sensitivity. Had they seen that, probably would have blown their mind. I actually don't know. They probably would have thought it was just noise because they only had one detector in Cleveland. And if there was only one detector, I don't know that we would have been as confident there was a real signal.
But with LIGO, if we'd had this result then.
If we had this result then, I don't know what people would have made of it because there was no concept of space-time curvature. There was no concept of gravitational waves. I have no idea what they would have made of it.
They were looking for exactly this. They did have some sense of curvature. They just didn't have space-time, the modern conception.
Well, they were looking for something a little different. They were looking to see whether there was a difference between what happens when the interferometer is oriented in this direction versus oriented in this direction. Whereas the signal that they saw all takes place with one orientation, and the interferometer just started to vibrate. Michelson and Moore were looking to see whether the arm lengths would change if as the orientation of the detector was changed. But I have no idea what they would have made of it had they seen something.
I got you. You're good.
So do you think there's an E equals MC squared waiting out there that will equate dark energy and dark matter?
Well, there is some energy density in the dark energy. Mm-hmm. So there is some equivalence between the mass of the dark energy and its energy, but I don't think there's any correspondence. There's no obvious correspondence between the density of dark matter and the density of dark energy.
Sure. I'm really struck by the declaration that there's the loss of 3 solar masses in the combination of those 2 black holes, and I've got a couple questions on that. The first is, given that that's based upon the energy coming out of the gravitational waves, so it doesn't have to necessarily be 2 black holes. I mean, if it was the black hole and really anything else, it would just be on a smaller scale, correct?
That's right, yes.
And then my question on that would be, brings to mind Hawking radiation and the idea of black hole evaporation, but if there's 3 solar masses that are getting pulled out based on gravitational waves, I feel like Hawking radiation really pales in comparison to whatever might come out of just the gravitational effects.
Well, it depends on the mass of the black hole. If for some reason there were black holes that had a mass of 1,000 trillion grams, 1 trillion kilograms. So if there was a black hole that had a mass of 1 trillion kilograms, it would Hawking evaporate in less than the age of the universe. And the vast majority of that energy would be released in a very short period of time. Now, the total energy is very small compared with the total energy that's released in the black holes that they've seen, but that's because those black holes are so much more massive. When a black hole explodes via Hawking evaporation, the entire rest mass energy of the black hole, as far as we know, would be released in radiation. Here, it was just a measly 5%.
Okay.
But I should say the energy radiated, that 3 solar masses of energy was radiated in 1 millisecond. And during that millisecond, this one system was more luminous than the rest of the universe combined, than all the other stars in the universe combined.
Yeah. There's a couple more questions. We had this gentleman in green here, or that there?
This nice
There.
lady first.
There we go.
Well, my question was just,
You haven't talked about the speed of gravitational waves at all. Do you think about that?
So general relativity predicts that gravitational waves propagate at the speed of light. And we now know that prediction has been verified because there was an event in August of 2017 where there's a gravitational wave signal seen from the merger of either two neutron stars or a neutron star and a black hole. And the neutron star merger, neutron star black hole merger, some of the material from the neutron star was ripped out, and there was a very visible, a very bright and visible explosion. And so this event was detected by a huge array of telescopes simultaneously with the gravitational wave detection. So we saw this one event in gravitational waves and simultaneously in electromagnetic waves. And so from that we know that they do propagate at the speed of light. So this event was astounding. So the gravitational wave observatories alerted the entire astronomical community. Anybody who had a telescope found out about this, and anybody who could pointed the telescope at it. And as it turns out, one of NASA's satellites, the Fermi satellite, detected a gravitational wave burst simultaneously and independently. And then other telescopes like the Hubble Space Telescope was as quickly as possible pointed at that region of the sky. All these ground-based observatories, radio telescopes, all observed that part of the sky. And the papers that resulted from this one event, I think 1 out of 3 astronomers in the world had a name on one of those papers. And I got a call from some reporters, and I asked them, how come you're not calling me about this? Because I'm not really an expert on this kind of thing. And they said, well, you're the only person we could think of who wasn't a co-author on one of the papers. Were you a co-author on one of the papers?
I was not.
So if there's another astronomer in the room, they were the... Yeah, half the people in this building were co-authors on one of the papers.
Okay. Things have been moving around in our solar system and bumping into each other since time immemorial. I mean, supposedly we were belted by a Mars-sized planet in the past. With what we can conceivably build in the near future, how small an event could we see?
That's a good question. Nobody has really thought of any other plausible astrophysical source that would produce a gravitational wave signal involving an object any less massive than a white dwarf, which the white dwarfs that exist typically have a mass of about 6/10 the mass of the sun. The way that the general relativity works, the strength of the signal, the gravitational wave luminosity, decreases very, very rapidly as you decrease the mass of the system, and also as you decrease the density. So black holes are the densest possible object, and those give us an observable signal if they're very, very massive. But once you go to something like a star, an ordinary star, or a planet, it's so diffuse that the signals conceivable signals are way too weak to be detected.
Okay, so I think we had one last question over here, and then we got to cut it off. Irini is here to take people across the street for the observing, so we'll catch that.
Does the expansion of space-time affect the LIGO measurements and interaction?
Yes, it does, and it is one of the problems we have. So the expansion of space-time affects the gravitational wave signal in that the binary black hole system is moving away from us. And so the gravitational wave signal is Doppler shifted or red shifted relative to what it is when it is emitted. And given the equivalence principle and the way general relativity works, there's a degeneracy between two black holes that have, say, a mass of 30 solar masses and that are at some distance, and two black holes that have, say, a mass of 15 solar masses that are at a closer distance. But there are ways to break that degeneracy.
Okay, so I hope you have plenty to think about from here. This is the questions and the comments online have certainly shown that Marc has taken us new places here tonight. Irini Lambridis, you want to be over here to take people because you can go out that door over there. So if you would like to go across the street to do the observing, Irini, join Irini over here. Our next talk is the third Thursday, January 15th. And let's give Marc one more hand of. So right, it was Caltech, and then yes, I got to run. I don't know what it was. Well, I was vamping a lot before. Yeah, we got things. January 15th.